like to thank another member of my organizing committee, that's my dear colleague Carlos Ventura, for his sincere and tremendous support in helping us organizing this particular symposium. He sends his sincere regret that he's unable to make it here in person, but he sent his very best for our successful event today. Okay, one last thing. I would like to make sure that all our financial sponsors are properly acknowledged. This including the University of British Columbia, Tongji University, of course. Thank you for all flying here. ERF, the Electrical Engineering Research Facility here at UBC. CSIM, thank you for all flying all the way here and adjusting your time to work with us. Department of Civil Engineering UBC has provided us support, and Canadian Association of Earthquake Engineering. And we also have professional engineers and geoscientists of BC, Structural Engineers Association of British Columbia, George III & Son, which will provide us with the material for demonstration on Wednesday. If you should have time, I would highly encourage you to attend a laboratory demo on Wednesday. And of course, Starbucks, who has sponsored us for all the coffee for all this symposium. So with that, I would like to quickly close my welcome remark, and thank you all for joining us today. Thank you. Okay, thank you. Now, I would like to welcome our Consul Mao from Chinese Consulate of China to actually come in here to give us a brief welcome. Thank you.
Good morning, ladies and gentlemen. It's really my great pleasure to be here, to be invited here today. And first, on behalf of Chinese Consul General in Vancouver, and to extend my warm congratulations to all of you for this opening of this symposium. And my special thanks to both Chinese and Canadian professors, students who have made great contributions to this collaborative project. As you may know, with the populations of 1.3 billion and its fast development of industrializations and urbanizations, China is facing unprecedented challenges on major disaster mitigations and prevention. Earthquake is certainly one of the most devastating disasters in China. To address those challenges, two major efforts have been made by the Chinese government. First, a nationwide public emergency management systems have been put in place, which consists of emergency rescues and recovery system, and a nationwide unified command and control systems with full functioning of quick response, high efficiency in operation, and full integration of emergency resources. During the Wenchuan earthquake in 2008, these systems have demonstrated its excellent functioning in disaster rescue, mitigations, and recovery. Another efforts have been made at prevention. The Chinese government recognized that science and technologies plays a crucial role in disaster prevention and mitigation. In 2006, the Ministry of Science and Technology has set up a special project on the study of high-risk earthquake areas mitigation and prevention, which included the study of buildings, construction, and structural standards for high-risk earthquake areas. The Ministry of Science and Technology also strongly supports our research institutions, universities, to collaborate with the top funding institutions, research institutions, and universities to address those challenges. In fact, the ministry has special funding support program for such kind of joint research projects. So I'm extremely happy to be here today and try to show my support. As a Council for Science and Technology in our consulate, my role actually is to try to promote such kind of collaborations with strong support from my ministry. Actually, I was assigned by the Ministry of Science and Technology, not working for the Ministry of Foreign Affairs. This is our system. Tongji University is one of the top-ranking universities in China, and I guess it's very famous for its civil engineering. Actually, to my relatives, my aunts are actually from this university. And UBC is one of the most prestigious universities in Canada. So I strongly believe that such kind of collaboration will help China to improve our national earthquake mitigation efforts. In this regard, I wish the symposium will be a great success. Thank you for your attention.
Okay, so let me quickly introducing the chair for the next section. In order to save time, the chair will be making sure that I'll leave it to the chair. Professor Adeban will decide when you finish. Okay, Professor Adeban, please.
Do you have that wireless?
Yes, thank you.
And you want me to open that?
If possible, thank you.
Yes. Okay, well, good morning, everyone. And let me start by adding my quick words of welcome to all our visitors here at UBC. First of all, the visitors from the West, Tongji University in China, and our visitors from the East, from Ontario, and the Far East, Quebec. So welcome to all our visitors. And I actually consider myself to be a visitor here today because I'm on sabbatical and have been for the last month and a half, and I had trouble finding my office this morning. And that's either really good or really bad. Either I'm really getting into my sabbatical or the beginning stages of Alzheimer's. I haven't figured out which one it is. But anyways, I'm a visitor here today, and my thanks to the organizers of this symposium. So our first speaker today is also our co-chair. But before I get to introduce him, let me just say that Dennis Mitchell and I discussed it, and we think what we want to do, and we talked to Tony Yang, is we want to move the photo session, which is scheduled for 30 minutes, from 10:15 to 10:45. We're going to move that to after lunch, and we'll leave it to Tony Yang to organize that. So we're going to skip the photo session, go directly to the coffee break whenever we finish the talks this morning, and then come right back, hopefully back on schedule around 11 o'clock with the next session. Okay, so that's the revised plan. So at this point, let me introduce our first speaker and the co-chair, Professor Dennis Mitchell from McGill University, who I'm sure is well known to most of us. Dennis.
Thank you, Perry. Oh, sorry. We're having computer problems here. Oh, dear. It's froze. I hope Perry hasn't subtracted that off my time that I'm allotted. Good morning, everybody. It's a pleasure to be here and be part of this wonderful symposium. And just to point out, we're really proud to be involved as a co-sponsor. That is the Canadian Seismic Research Network. It's a wonderful idea, and we're looking forward to the next 3 days. I'm going to be talking about deficient existing shear walls. And we have many examples in past earthquakes. I'm just showing one here, and that's from the Kobe earthquake in 1995. You can see, you can see that clearly it's a shear failure. It's a thin wall. There's no confinement at the end. It's about 150 millimeters thick. There's inadequate amount of confinement reinforcement and concentrated reinforcement at the ends. Inadequate amount of, obviously, shear reinforcement. But even if it had shear reinforcement, it's difficult to actually anchor that shear reinforcement at the end if there's no concentrated reinforcement at the end. So that's one type of really severe problem, which was very prevalent in the construction of many shear wall structures in Canada in the 1960s, thin shear walls. And the problem is that they have lap splices in critical locations at the base of the wall. There's inadequate shear reinforcement. It's typically, as I mentioned, poorly anchored at the ends. The confinement reinforcement typically doesn't exist. and therefore you get a very poor response. And back then, they weren't really concerned about earthquake design, unfortunately. So we've done a number of tests at McGill University. This shows the test setup that we've been using. We have typically a reverse cyclic loading at the tip of the wall, and the wall is fixed at the base. Notice that we're testing it in the horizontal position for the ease of testing. This is post-tension to the strong floor, and then we have guides here to prevent lateral movement. The series that we just finished some time ago involves lap splices at the bottom, the most critical section of the shear wall of 30 bar diameters. We typically use 20 M bars in these fairly thin walls. They're 150 millimeters thick. And this is very symbolic of the problems that exist in current construction. And one of the problems when you have a very thin wall, 150 millimeters thick, is that there's no way to anchor the horizontal reinforcement. So typically they would put a 90-degree band without bending it around the reinforcement at the ends of the walls. And of course, that's totally inadequate. We did 2 walls in the as-built condition, one wall with 2 20Ms at each end, and one wall with 4 20Ms at each end. And these have the lap splices, and they have typical amounts of vertical and horizontal uniformly distributed reinforcement. The way in which these 2 walls failed, W1 with the 2 20Ms, had failure of the lap splices at the base of the wall, as you would expect. The W2 test with the 4 20Ms in the critical section has the lap splice splitting failure in between the 2 levels of 20 M bars. You can see the close-ups in the bottom of the figure showing that these failure planes took place in slightly different locations because of the difference in the flexural reinforcement. The responses of W1 and W2, they didn't reach yield. And, you know, if it were monotonic loading, they may have reached yield and had some ductility. But because of the reverse cyclic loading, we get a brittle type of shear failure. We get inadequate amount of energy dissipation, both for W1 and W2. W2 had a larger amount of flexural steel and therefore has a higher capacity. But both of these are inadequate in terms of performance. Now, just wanted to show you what one of these tests looked like. We're loading up and down on the right-hand side, and you will start to see the flexural cracks forming. And then you'll see some shear cracking, inclined shear cracking forming. And then eventually we'll see the lap splice failure in this region here. Now, it didn't move very much. It's not very ductile. So this is the brittle type of failure you get with this type of construction. Well, we looked at a number of ways of improving this. As I said, the walls were tested in their horizontal position, and we used carbon fiber wrap. We rounded the corners, we roughened the surface, and then you can wrap the carbon fiber around the walls. It's a very easy solution. We did it over the probable plastic hinge region with a little bit of extra. We used the carbon fiber wrap with the fibers in this direction, of course, in strips as well to give improved shear response. And when we look at that, we see a much improved response, as you can see here. But still, it's not excellent. The one with the 4 20Ms at each end is over here, 2 20Ms at each end of the wall over here. But it is improved response, quite significant improvement. And maybe for some retrofits, it would be adequate. The other type of retrofit that we did was a more serious retrofit job. In fact, we took the 2 specimens that had failed under reverse cyclic loading and actually repaired them but it's also representing a retrofit procedure where we put some fiber-reinforced self-consolidating concrete over the lap splice region, adding it to the wall, not lengthening the wall because architecturally that's sometimes very difficult to do with the retrofit. Then above this, we have the CFRP wrap and we have the shear straps. In terms of the retrofit, it's quite a serious job. It involves removing some concrete at both ends, putting hoops around this area here, and not lengthening the wall, however, because this is removed concrete that's being replaced with the fiber-reinforced self-consolidating concrete. And we have through bars, which give the shear connection as well, and we have longitudinal reinforcement, which increases the flexural strength to make this a capacity-protected zone. So that's what it looked like, and a photograph of the retrofit here. You can see that we used headed bars going into the foundation wall to get really good anchorage of this longitudinal reinforcement. This surface was roughened, headed bars again, and here are the through bolts going through the wall to give adequate shear connection. You can see the top view over here. So that is now a capacity-protected region, and when we do that retrofit, we see significantly improved responses, and this could be used for certain cases if you're looking at retrofit. Well, we also looked at a 5-story prototype structure to be able to predict what these different retrofit scenarios would give us. And so this 5-story structure had 12-foot high story heights. We're using the imperial units. It's 1960s construction. It's a shear wall frame. We have deficient shear walls, the thin shear walls with inadequate anchorage of the shear reinforcement and lap splices at the base and at each story. It's a frame associated with it which has limited ductility, so there again is a problem. We would like the walls to protect the frame. We looked at 2 different locations, putting this structure in Montreal and having the same structure in Vancouver. The wind loading, which would have governed the design back in the 60s, was fairly similar in Montreal and Vancouver, so you could have had very similar structures in those 2 cities. We used a uniform hazard spectra for 2% in 50 years for Montreal and for Vancouver, as well as the 10% in 50 years to look at different performance requirements from the walls for different seismic hazard. And we developed the fiber models to predict the response of the walls. Here we can see the fiber model versus the test, which is in the light shaded area there. It's difficult to get a really good, accurate fiber model for the case where it's extremely brittle, but it was fairly close. For the CFRP retrofit, the wrap solution, here's our fiber model in red, and the light gray is the experimental results. And then for the more severe retrofit, where we're using fiber-reinforced self-consolidating concrete as well as the fiber wrap, we see much improved response and the predictions of the fiber model versus the experimental results. The conclusions from these analyses, we did the nonlinear static procedure, which involves a pushover analysis. It's, of course, nonlinear, using the fiber models, and we used the nonlinear dynamic procedures as well, with a suite of 12 earthquakes for each analyses. And the results are rather interesting, and it worked out rather neatly. For the as-built condition, the structure is no good. It doesn't have adequate performance for either Montreal or Vancouver. And when we performed the CFRP retrofit, which is a very easy retrofit procedure to accomplish, It was okay for Montreal, but it was really on the limit for Vancouver. And it was questionable as to whether you would accept that or not. And of course, with the fiber-reinforced self-consolidating concrete retrofit with that protected zone at the base of the wall, it was okay for both Montreal and Vancouver. These are the results for the 2% in 50 years. The other type of wall problems that we've seen in Chile involve thicker walls, but very poor anchorage details of the horizontal reinforcement, the shear reinforcement, and inadequate confinement at the ends of the walls, and using these 90-degree bends which pop open during an earthquake. We also experienced wall buckling in the Chile earthquake because of the slenderness ratio of these walls. And the walls that we examined varied from 175 millimeters to 250 millimeters. And you cannot put confinement reinforcement in a wall that's less than about 200 millimeters. It's just impossible. You'd have to have a jeweler make the cage to put a confinement reinforcement cage in at the ends of the walls. So these are the details that existed for the Chile. There's no confinement reinforcement. There's the 90-degree bend anchorages. And this is what we would use for our very ductile walls in the CSA standard, having confinement and having this horizontal shear reinforcement well anchored in a confined region. And it takes me back to this building that was being evaluated in the year 2000 by an up-and-coming firm, Tipping and Marr, out of California. And their problem was that they needed to retrofit this building. It has two shear wall cores, coupled walls in this direction and ductile walls in that direction, but they weren't actually ductile. They had lots of problems with the detailing. And then the floors are hung off the top of the building, so that it's very clear that the structural seismic force resisting system are the shear walls. I mean, that's the whole meat of the structure in resisting lateral loads. And so we helped this particular project out by carrying out a series of tests to mimic the poor details in the shear walls and look at ways of improving those details. And one of the aspects that we were looking at is, can we improve lap splices by pinning through the wall and being able to prevent the splitting type failures that occur between the bars. So we carried out some tests at McGill University. This shows the cross-section of the shear walls, and let me point out that there were 90-degree bend hooked anchorages at the ends. Now those would open up in severe reverse cyclic loading, but these sorts of details are similar to the ones we saw in Chile. They have the same sort of deficiencies. There's no concentrated reinforcement at the ends either. And so we were looking at lap splices at the bottom of the wall here in this particular case. And we did a number of two different types of specimens. The problem is in the shear wall that they had, of course, you've got lap splices at the base and at every floor level. So we were simulating the lap splices at the base with this test, and we were moving the lap splice up higher to look at this case, still in a very high moment region, but perhaps getting some yielding at the very base. So we looked at those two different scenarios with these very poor details of the reinforcement. And interesting how it turned out, we saw that with the 90-degree laps at the base, this is the hysteretic response. Not the greatest, ending up with lap splice failures. They had 36 bar diameter lap splices for all their lap splices. And interestingly enough, when you move the lap splice up a bit, you get some improvement in the response. So we were looking at, they really wanted to make sure that there were no problems with these shear walls. So we looked at retrofit procedures, and we used again in this case we weren't using self-consolidating concrete or fiber reinforced concrete, but we were looking at a reinforced concrete addition at the base over the lap splice length. And we were looking at the other specimen where the lap splices were up here with just the carbon fiber wrap. And we also used headed bars at the ends to help improve the confinement and prevent the popping out of the hooks of these bars. And we used these end confinement reinforcing in the carbon fiber wrap solution as well to look at an improved response. So it's a combination of, at the base, looking at extra reinforcement in concrete and looking at carbon fiber wrap plus headed bars, and headed bars through the thickness at the key locations where we have lap splices. This is what the specimens look like. This is with the full retrofit at the base, and here you can see bands where we're trying to improve the lap splices and give shear resistance. Excellent response. And this is the case here where we've got the lap splice in this region here where we're using just the carbon fiber wrap plus the pins going into the wall. And again, we get excellent response. So that was a very interesting project to work on, and just looking at something that now appears in the current draft of the 2014 CSA Standard Design of Concrete Structures in Clause 21, which gives the recommended details for reinforcement for different ductility levels. And we do permit the 90-degree hooked anchorage for a ductility ratio of 1.5. We do insist on some confinement at the ends of the walls. As you move the ductility up, you can see that the detailing becomes more stringent. We have a U-bar here with a lap splice away from the critical end regions. And for the ductile walls, we prefer to have the horizontal shear reinforcement well anchored in the confined region at the ends of the wall. So thank you very much for your attention.
We do have time for a couple of quick questions. Thanks, Dennis, for staying on schedule. Any questions? I have a quick one for you. The fiber reinforced self-consolidating concrete, is it actually, I mean, once you put fiber into that self-consolidating concrete, is it still self-consolidating?
Yeah, well, it's interesting because what we do is we've done a lot of work with different volume fractions of fibers. We're using 0.5%. And when you use 0.5%, instead of getting the flow from the slump flow test, it looks more like a slump test when you've got the fibers in there. So I think the thing is that we can use fibers and still get workability, and that was the idea of using fiber self-consolidating concrete. We use that concrete to get some workability.
But it definitely needs more work to make sure it's consolidated properly with those fibers.
Yeah, you need a little bit of work, yeah, a little bit of vibration. Yes.
Any other quick questions? Yeah, please.
Thank you very much. And I just have in the first picture, and at the end there is a hook or without a hook.
There's a 90-degree hook here.
Yeah, 90 degree, and at the end I saw the hook, but I saw the test specimen maybe without this.
Oh, yes, absolutely. The tests we were doing were trying to mimic older construction, poor details. But this is what is recommended in the current draft of our new code. So, of course, they're excellent details.
And according to your suggestion, the RD is also just 1.5?
Yes.
Oh, yeah.
Right.
If the hook is outside the longitudinal bar, there will be large to 4.0. the last picture.
Yes, well,
The
they're lapping here. That's right.
The third.
So you get good anchorage
Yeah.
in this zone here.
Okay, thank you.
Okay.
Thank you very much.
Great. Well, thank you, Dennis.
Well, it's my pleasure to introduce the next speaker, Perry Adebar. And Perry is chair of the Seismic Design Subcommittee of the Canadian Concrete Code, CSA A23.3. And I understand that Perry is going to be talking about the research that built up to some of the changes that have been proposed in the current draft of that code. Perry?
Great. Thanks, Dennis. In addition to being a member of the seismic subcommittee of our Canadian Code, Dennis is also the chair of the whole committee. So, and the research I'm going to talk about is work that was done as part of the CSRN, Canadian Seismic Research Network. So, and Dennis was our lead investigator on that. So, I want to acknowledge Dennis. So, I've got quite a few slides here, and I'm not going to show them all. I'm going to have to stop at some point to stay within the limit. And Dennis, you can always wave at me if I'm going a little bit too long. But I'm just want to talk, as Dennis mentioned, about some of the research we've done here at UBC, my students and myself, that have led to some changes in the code. And I've got a long list there. As I said, I won't necessarily get through all of them. They are related. They're not 6 separate topics, but somewhat related topics, and I'll go through them and see how I do. First of all, our code is going more and more towards displacement-based design for concrete shear walls, and therefore you need to estimate what your displacement demands are. And to do that, typically we use a linear dynamic analysis, and we need to use an appropriate flexural rigidity to account for cracking. And this is an expression that's been around for a long time. And when I first looked at this subject, I thought it was a great expression. Actually, Tom Pauley came up with it. And it's currently used to analyze buildings and to estimate displacements. So using about a 30% reduction. What's happened there? It's coming back now, I guess. Is it? So Dennis, you've stopped the stopwatch, have you?
Oh, no, I haven't.
Anyway, so you're typically using a 30% reduction on the flexural rigidity based on an uncracked shear wall. So you're using 70%. That's a very typical number that we're using today. And we've done quite a bit of work on this. And in fact, a lot of the work I'm going to show today comes from Hassan Dizdar, who's actually sitting in the room here. Put your hand up, Hassan. A lot of the work you'll see here is actually coming from Hassan. So hopefully this isn't going to keep happening, is it? I keep hearing there's like a tone or something. I see this is the first time we're using the other laptop. Is that the problem? Anyway, so we've been investigating effective stiffness of, can I use that or should I use this instead? Okay. So we've been investigating this for a few years now, and this is a load deformation response of a typical shear wall. Okay, and if you look just at the loading envelope, actually the idea of using that expression as a function of the axial load makes a lot of sense, because here's what the load deformation responses look like for a number of severely cracked walls. And a wall that has high compression has a loading envelope that's actually quite steep and goes up quite high. And if you have low axial compression, you crack much earlier and you get a much softer response. So that's where that equation comes from and actually makes a lot of sense. But if you look at the full response, and in particular if you look at the hysteretic response, what happens is a wall with high axial compression has very little energy dissipation, because when you take the lateral load off, it stands up straight. Whereas if you've got lower axial compression, you dissipate more energy. You get more hysteretic damping. And that turns out to make a huge effect. And here are some analysis we've done. And these are a simple single degree of freedom analysis, many, many different shear walls. And the really interesting point is the walls with the highest compression have the lowest effective stiffness. So in other words, what we have in the code right now has it exactly wrong or exactly backwards. Actually, a wall with a high axial compression will generally have a lower effective stiffness because it'll dissipate very little energy. It's like a rocking mechanism. Okay, and looking at really the strength of the wall as a ratio of the elastic demand is the right way to go. And here are some results from Masson, from nonlinear analysis of essentially full buildings. Oops, still doing that. And what you see is that instead of relating it to the axial compression, what we need to do is relate it to the strength. Any idea what's happening, Stanley, or no? I don't know. Yes, Tony. Nope. You're gonna do it while I'm speaking with us? Yeah. Okay, that sounds great. Anyway, so again, just to summarize, what you want to do is relate the effective flexural rigidity to the strength rather than to the axial load. And in fact, here's the expression at the bottom that's been proposed for the code and is in the code. And just to simplify it, we've said in the code, one of the simplifications the committee came up with is saying we can assume that the RO is equal to the overstrength. And so you end up with a very simple expression where the effective stiffness is a function of the RD value you use to design the wall. So if you've got a moderately ductile wall with an RD of 2, we're talking about 0.65, so that's a reduction from 0.7. And if you've got an RD of 3.5, we're down to 0.5. So very important, this new expression means generally you have lower effective rigidities of shear walls and therefore larger displacements. And indeed, even our seismicity is going up here on the west coast, so our displacements are going up. Yeah, well, it's okay. The next topic I'm going to talk about, so that's it for effective stiffness. The next topic is thin shear walls. Dennis talked about thin shear walls. And I'm going to focus in on one failure mechanism, which is really flexural compression failure of the walls. Dennis talked about anchorage and lap splices, and I'm going to talk about some of the work we've done on the problem of flexural compression failures. And show you some test results and show you the basic failure mechanism. We've done little wall elements, but we've also done various columns and larger walls, and we're seeing this one, what I would call a compression failure mechanism, occurring when the elements are thin. So we're not actually using that one, are we? That's Dennis's, right? That's the one I've been using right now, right? Maybe we do want to use that one, yeah. Well, yeah, I've got it right here on the stick. Should I just... I got it right here. So there's a video. Maybe disconnect that one because we're not using it right now, right? Dennis is finished, right?
There's a switch that switched it off.
Oh, okay.
Switched it off. But if worst comes to the worst, I'll hold that up on mine.
I could talk about Dennis's work. Sorry? Yeah, okay, I won't miss that part at the end. There's a bit on rocking foundations. Okay, yeah, thanks, Liam. Actually, Liam, all the work I've done is original work. What did you just say? It's oh, right. The rest of it's not very original, just original. Thanks for that, Liam. No, I don't. No, there's no video. There's a few tiny animations, but one I just... No, I can't be doing the problem, right?
You want me to load it up anyway, just in case.
Yeah, copy it on there. Maybe I'll just start with yours. And sorry? Yeah, we can work like that. Sure, people can see it, right? So it works better if we just stay like that? No, it doesn't. It does the same thing, right? Yeah. Let's switch to Dennis here. Can you switch it to his computer? Okay, so let's hope for the best. Thanks, Dennis. So you can start the clock again. Okay, so Dennis talked about some of the observations from the Chile earthquake, and I'm going to talk, as I said, a bit more about some thin wall failures. Here's an example of one that's really a column/wall, but it was thin, and these are typically 150 millimeters, a lot of them. There's another one that failed at the end of a shear wall, another shear wall, crushing all along the end of the wall, and here's another example. So as Dennis already mentioned about the lack of confinement, and anchorage issues, but as I said, I want to focus on one failure mechanism, which I believe is very important, which is flexural compression failure of these walls. And these were some little tests we did at UBC, and this is what the specimens looked like. And I just want to focus in on two of them, the type 3, which has some very nominal ties, not what you would call confinement ties, but very light ties, the kind of thing you'd put in a non-seismic element. Right? Just minimum column ties. And the type 2, which doesn't have anything connecting the two layers of reinforcing steel. And there's two layers of small bars in a 150 millimeter wall, which is what we saw in Chile. And here's exactly what you might expect. The type 3 elements, the response looks like a concrete cylinder response. You get out into strains of 4 parts per thousand before it finally crushes. And even then, it's quite reasonably ductile. So very nominal ties, very light ties, makes it behave like we sort of hope it would. And these elements are in pure compression. And here's a type 2 element, which we've started to load up. Okay, and there's none of these nominal ties. And we get up to this point, we've got it up. So far, everything looks great. We're up to 30 MPa average stress on these elements. So we're getting close to the peak compression strength. Here's what the element looks like. Okay, and if you look closely, you can see a little bit of damage at the middle there, but all of a sudden, it completely explodes. And we saw that when the first time it happened, I thought there was something wrong with the test setup, and when we saw it happen many times, we realized there really is a phenomena here. And here are some photos of a couple of specimens, and it's the one on the right that I really want to focus on, because I think it really explains the failure mechanism. And I guess I have a pointer, but I'll use this one. So if you look here, here's a horizontal bar, okay, vertical bars there, and there's another horizontal bar, and there's a failure crack connecting these reinforcing bars. And that's very typical of what we see. When you've got a narrow element under high compression, we get this complete failure plane going right through the element. And there's just a bunch of the summary of the tests we've done now over a few years, getting as low at the strains. If you look here on the compression strain capacities, as low as less than 1 part per thousand when the elements get more slender. Okay, now we've also done a study on really columns and walls. These are gravity columns and gravity walls. These are the 4 column specimens. We also did a 5th specimen like the bottom one, but without the cross tie, so it's a wall. And if I just quickly look at some of these results, if we look at the top 2, okay, I was surprised to see how tough these gravity columns are. These are gravity columns with nominal gravity ties, not seismic detailing, and we couldn't break them. Okay, if we focus in on this column, and we look at what our predicted displacement capacity was, the capacity, it was much greater from the experiment. Essentially, we couldn't break it. Okay, we crushed all the concrete on the outsides, but it still carried the load, and it had a heavy load, 33% of F prime CAG. And the reason why it works so well is because in this middle zone here, you can crush all the concrete here and here, but this middle zone, which has some nominal ties around it, continues to carry the gravity load. So we were really surprised at how good some of these gravity columns can be. And that's, of course, great news. But these elements have a certain dimension to them, like the square ones, or they have rectangular shapes where it's like no more than 3-to-1. Once you get to the slender walls, once you start getting to 4-to-1 or 5-to-1, it's a completely different animal. And what we see happening in those is exactly what we saw happening in those little element tests. And here's an example of the wall specimen. We're loading it up, a little bit of damage. All of a sudden it goes bang, and it's gone. Complete load capacity is gone, and the failure mechanism is exactly like that element. It goes right through the thin wall and completely loses all its axial capacity. And to me, that's a big worry, because as Dennis mentioned, we've got a lot of these thin walls around, and even today, people are building 6-inch walls in Vancouver and high-rise buildings as columns. Okay, it's not unusual in Vancouver. Not every engineer, but some of them are. Here are some of the changes that we've made as a committee to address this issue. Number one, in Clause 10, we've reduced the axial compression capacity of thin elements to reflect that failure mechanism that I just talked about. So you got thin elements that you don't want to be loading them up too high. Okay, right now people are loading them up much too high because they don't have the toughness. Okay? The other thing, we've got to be really careful of limiting the compression strain. I'm actually not a big fan of confinement. A lot of people think you got to confine everything. I think you just got to avoid the large compression strains, and then you don't have to confine it. Okay, if you're going to have high compression strains, you've got to confine. If you keep the compression strains low, then you don't actually need to confine. Significant. You do need, as Dennis showed, some sort of nominal ties at the end. That nice diagram Dennis showed at the end there. Okay, and the other thing we've got to watch out is because we have a lot of thin walls and buildings that people call bearing walls that I worry about are going to fail in a seismic event. Okay, so that was thin walls. So Dennis, how much time do I have? I've got to figure out. Okay. I think I got another 20, right? So, okay, this is just a quick topic so that Patrick and I can have a debate over lunch. This is a topic that Patrick and I have discussed, and it's an interesting topic. 5-6 years ago when we were starting work on the code, I thought the biggest job we had to do was change the whole philosophy of how we design shear walls. And the current philosophy has been, traditionally has been, you provide a fuse at the bottom, and you put lots of special detailing down there, and then the rest of the wall you can have essentially conventional detailing. That's been the way we've designed walls. And that comes from thinking of it sort of as a first mode pushover response, because if you have this nice ductile hinge at the bottom, the rest will be protected. And of course, we've all learned that in tall buildings, you're going to get very higher mode bending moments near the middle of the shear wall. So here's an example of a result that one of my students has done, where there's nonlinear elements at the base of the shear wall, which is commonly done. And what you see is that you're developing in these moment envelopes from dynamic analysis, you're developing huge bending moments at mid-height. Okay, but that's because these elements are modeled as linear. So that's how these moments can get large. And 5 or 6 years ago, I thought, boy, we really got to change the code because we're going to develop hinges at mid-height, and that's a problem. Okay, well, we've done a lot of work on this, and one of the issues has to do with how you model the shear walls, and this is a theme through a lot of what I'm going to talk about in the next little while, is a lot of people have used a simple elastic plastic model. And that green line there is an elastic plastic model of a shear wall, using that reduced effective rigidity, your slope, and you end up with a yield point, which is the yellow dot. But real shear walls have a line that's something more like the red one. It's actually a curve, and it's closer to a trilinear response, where you have an initial uncracked response, and then you have a cracked portion of the response. And the yield curvatures then become much larger. And if you use that model to analyze the walls, what you see, and this comes from some of the Sands work, what you see is suddenly the problem really goes away. So what I'm looking at here in this diagram is the blue line the yellow line is the yield curvature for an elastic plastic model, and the green, dark green line are the predicted curvature demands from that model. So what you've got are curvature demands much greater than the yield curvature from that model. But if you use the trilinear model, then first of all, your curvature demands are the red line. They've reduced slightly, but much more importantly, the yield curvature has gone up a lot. So what happens suddenly by switching to a more accurate model is the problem, in my opinion, essentially goes away. Another big part of it is scaling. I won't talk about this, but these are all the same model, but different ground motions and different scaling. You get huge differences when you don't select and scale the motions appropriately. And again, if you use proper scaling, proper model, you get some very reasonable results. So this is a very busy slide. I just want to show you a very simple conclusion. This is a bunch of data, again, from a SAN, where we're looking at curvature demands for all different buildings. And this value right here of curvature times wall length, this is what we assume to be the yield curvature for the wall. In other words, most of the data is below what we assume to be the yield curvature. And in fact, if you look at the table on the right, in the bottom right corner, for the mean plus 1 standard deviation result, the curvature times wall length is less than a typical assumed upper bound yield curvature. Okay, so the summary from that is that, in my opinion, we don't need to provide special detailing at the mid-height of the shear wall. And in fact, we haven't added that. We do need to be careful primarily about these compression failures. And this relates to what I talked about earlier, that we don't want to have large compression strains in the wall. Okay, and some people advocate the idea of actually preventing the yielding, and I'm actually against that. I think a little bit of yielding at mid-height, at small curvatures, is a good thing because it helps reduce the shear demands. And speaking of that, I'll go to design shear forces very briefly. So our design shear force is our elastic shear force multiplied by a couple of things. Essentially, we adjust the shear force based on the bending moment. We use the same reduction factor as we do for bending moment. And then we amplify our shear based on the actual bending strength. That's something we've had in the code for a long time here in Canada, and it's very good. But there's another factor, which is an amplification factor to account for the fact that the higher mode shears aren't linked to the flexural capacity. And a lot of people have done work on this, including, again, Patrick and Robert Tremblay. I don't know if he's here yet, but Robert's done work on this. And many people have different solutions. My own conclusion is that a lot of the suggested amplification factors are too large because people have used a bad model and have used the wrong selection and scaling of ground motion. And here's an example, again, of the shear envelopes you get. The red line is the shear envelope from an elastic, perfectly plastic model. The blue line is what you get if you just simply use a trilinear model. So you get a significant reduction in the shear due to the cracking, flexural cracking that occurs near mid-height. And here's again a summary of the results that Hassan got from his work showing the shear amplification as a function of the strength of the wall and a nice little dashed line that goes through the data. And that compares actually very nicely. The green line there is from Hassan. The red line is work that Patrick has done. And the two results actually correspond very nicely, which I think is a great thing. And what we've done in Canada is we've gone to a reduced amplification factor. Instead of going up to 2, even though the data shows that we should go to 2, the code committee has agreed to go to 1.5 for a number of reasons. And here's a list of what are some of those reasons. First of all, we've seen very few shear wall failures in actual buildings. That the higher mode shear forces exist for a very short time. And by the time something starts to happen, the shear force turns around. Nonlinear analysis has shown that walls have shear ductility, right? And we've seen that in a number of studies. And an important one is that the maximum base shear force and the maximum base rotation, and the base rotation reduces shear capacity, they don't happen at the same time. Okay, and that the largest shear force that we're looking at there, that happens once in an earthquake, right? The next cycle typically, or the next highest shear pulse, will actually be significantly lower. Anyway, so there's a bunch of reasons why I believe you want to go with a low estimate of the shear magnification. Okay, I'm going to maybe just quickly go through. Dennis, how much should I go? Another 5 minutes? Okay, we're going to be fine. I should have had more slides. Okay, here's the biggest single change that we've done in the code is a new section on the design of gravity frames. And one of the things that we've done badly, if you look at the design of seismic design of buildings, is we identify a piece of the building and we say, the wall, that's the seismic force resisting piece. Let's do a really good job of designing that wall and making sure it's ductile. And the rest, well, that's gravity load system. Let's not worry about that, because it's not carrying the earthquake forces. And really the problem with this comes from the whole idea of thinking in terms of forces. And if it was a force problem, that would all be great. But here's a beautiful example. Here's the CTV building in Christchurch before the earthquake, and here's the CTV building after the earthquake. And the shear walls did beautifully. There they are. They're standing up, not damaged. But the rest of the building is gone, right? And so here's an example of where, and it's a complicated building, and we don't want to get into much of a discussion on it, but essentially the seismic force resisting system didn't protect the gravity frame, and the gravity frame collapsed and killed people. And it's still a major issue with the way we design buildings. We need to think about the displacement demands on the gravity frame system. And we've done a lot of work on that for our Canadian code. We have a very large new subclause dealing with this issue. And there's more work to be done. And I just want to briefly mention one of the important things is getting an estimate, a simple estimate of the displacement demands on the gravity frame. And we're doing that using the interstory drift demands. Okay, and here's an example again of San's work where the nonlinear analysis shows us what these interstory drift envelopes look like coming from nonlinear analysis, both from the mean and the mean plus standard deviation. And we've used these results to come up with a simple envelope, a bilinear variation of interstory drift. And at the bottom here, the envelope comes to a significant value here at the base, even though the results show that there's very little drift at the base when you only model the flexural deformations. But what's the differences in here are the shear deformations, which are very significant in a hinge. You get a lot of interstory drift in a plastic flexural hinge due to shear. Anyway, so what we've got in our code is a simplified method of analyzing the gravity frame by using this simple interstory drift ratio envelope that's defined in the code. And the way you come up with that very quickly is you use a linear dynamic analysis with your effective flexural rigidity, accounting for things like torsion in your building and accidental torsion, and it now says including foundation movements. So this is really important. Any movements in your shear wall foundation probably aren't going to hurt the shear wall very much. The shear wall is just going to rotate over, but it's going to put huge demands on that gravity frame. And just talk very briefly on some of the work we've done on foundation movements. Here are some results coming from the work of Purya Bazargani, who is one of my current PhD students. He's done many nonlinear analysis, different shear wall buildings with different size foundations on different footing sizes, different soil types. Okay, and these are all the different displacement increases you get. So we're looking at ratio of top wall displacement to the displacement from a fixed base model. How much does the displacements increase due to foundation movements? And the answer is it can increase a huge amount, as you might expect. What surprised us was that the capacity protected foundations, in other words, the foundations where you actually say you're going to make the wall weaker than the foundation, still gives you very significant movements. Okay? Once you, of course, if you're going to let the foundation rock, that is, you're not protecting it by the hinging of the wall, then you'll get larger displacements. And what we have in our Canadian concrete code, consistent with the draft 2015 NDCC, is a statement that says the increased displacements due to movements of foundations shall be accounted for in the design of the SFRS, and perhaps more importantly, in the design of the gravity load frame. So that's actually in our Canadian concrete code as well as NDCC. And now, how do you calculate those displacements? I'm not going to spend much more time on it, but what I'll tell you is we've been spending a lot of time coming up with simple ways to do that. So is capacity protected foundations? What our code says is you can use a simple static analysis that accounts for the bearing stress distribution and the stiffness of the soil or rock. And we've actually come up with, that's too bad. That was my favorite part. But here's an equation that we've actually put in the code. And it's a very simple equation that gives you footing rotations. And all it has in it is the bearing stress length, the G, the effective shear of the modulus of the soil. And it's not trivial to come up with an appropriate value for that because, of course, that's strain dependent, as well as the length of the footing and uniform, the magnitude of bearing stress, the G, the length of the uniform bearing stress, and the length of the footing. That's all you need to come up with a very good estimate of footing rotation. And I'll stop there. There's a little bit more about rocking footings, but I'll end there because I'm taking at least my time. Sorry about that, Dennis.
No, that was great. Sorry about the mechanical problem. We will unfortunately forego the questions because we've run quite a bit behind. The next speaker is Professor Nenny Panthea.
It's a good idea to be the third speaker. All the bugs have been worked out now, I think. Thank you very much. And first of all, thank you so much to you, Tony, for inviting me. I'm not an expert in earthquakes, so I think I was quite surprised. Of course, I'm very grateful that you invited me, but I'm not an expert in earthquakes. So I'd like you to sort of stop thinking in terms of meters and start thinking in terms of centimeters and nanometers and micrometers. So I'm talking about materials here. So we'll take a look at really how we can increase the energy absorption capacity of materials. And in particular, I want to talk a little bit about fiber-reinforced concrete here. So the key here is, although concrete crushing that we just saw in Dennis's slides and Perry's slides, I think we can perhaps do a little bit about not making them so brittle and increasing their energy absorption capacity by using fiber reinforcement. And if I may continue talking, one of the slides, I think, in fact, is a wonderful segue into what I'm going to talk about, was Dennis's work in fiber-reinforced concrete, which is self-compacting. And I was very pleased to see that, in fact, the fiber-reinforced concrete retrofit solution, in fact, performed the best of all the other retrofit solutions. It's a great segue into what I'm going to say. So just to give you a brief overview of what I'm going to talk about, fiber-reinforced concrete. Once you are not familiar with this material, I'll give a very brief overview of how fiber-reinforced concrete is produced. We are doing work here at UBC on eco-friendly ductile cementitious composites. These are essentially elastoplastic concrete materials with fiber reinforcement, but they're also eco-friendly, which means that we have tried to reduce the amount of cement in these systems so that we can reduce their carbon footprint. I'll talk a little bit about the infrastructure deterioration and interest in durable cementitious composites. When you're analyzing these structures for seismic response, sometimes it seems that the fact that these structures can be quite deteriorated seems to not be considered, and hence I think one area one needs to perhaps look at is how deteriorated a structure is as a result of corrosion or other cracking or other deterioration mechanisms, and how it may actually, in the overall scheme of things, affect its seismic response. And then coming from there, I'll talk a little bit about the FRCs, which are smart FRCs, which can be utilized for sensing and for smart structures. Okay? Oh, perfect timing. Thank you. So fibers which are going to concrete are of several types. You have steel, polyester, high-density polyethylene, cellulose, carbon, basalt, and the list goes on. There are a number of fibers that are produced. It's a huge industry, almost about 500,000 metric tons of fibers that are utilized in concrete these days. Fibers are basically directly added to concrete. So when you add fibers to concrete, you will see fresh concrete, which will look a little bit like that. It can be done by 4 different methods. One would be to just add directly to concrete. You can also shotcrete these materials, so you can actually spray fiber reinforced shotcrete. So you can see this person who is spraying this material in a retrofit project. You can also produce SIFCON. SIFCON is a material where you produce a bed of concrete and then you add bed of fiber, and then you would actually pour cement slurry. Now, defense uses a lot of this material because it's highly, highly energy absorbing material. And finally, you could also produce it by the spray process. So this is how a lot of GRCs, glass reinforced cement products, number of buildings on the campus have GRC cladding. So these are how these materials are actually produced. The crux of the matter, in fact, at the sort of the primary mechanism by which you can actually make a material absorb a lot more energy is by the fiber bridging effect. So basically, if you have concrete which does not have fibers, once you have a crack, this crack would have very low stress carrying capacity. The moment you have fibers in there, what that means is you have essentially a stress carrying capacity across a crack, and this is what we call a residual tensile capacity or residual compressive capacity. So you would have basically this kind of a response. In terms of applications, number of, as I said, it's a very large industry now. This is the John F. Kennedy Airport in New York, fiber reinforced concrete runways. Wave breakers, again, fiber reinforced concrete, no other reinforcement in them. This is for erosion prevention in a hydraulic structure. And these are heavily loaded industrial floors, for example. They are generally produced with fiber reinforced concrete without any construction joints. Also, architectural concrete, you'll see this is the Princess Palace in Saudi Arabia, fiber reinforced concrete, GRC in this particular case. This is the Salmon River Bridge in Halifax, again a fiber reinforced concrete deck with no other traditional reinforcement. Refractories, they use a large amount of fiber reinforcement. Precast products, this is the Al Shahid Monument, again carbon fiber reinforced concrete. Precast products, which are materials which are actually attached onto a skeletal structure. These panels again are fiber reinforced concrete. This is a golf course in Dubai. Permanent formwork. This is again a formwork which is made with carbon fiber reinforced cement, and you produce the formwork, you pour the concrete, and you basically go away. You do not need to remove the formwork. Again, an application from Japan. This is the St. Lucas Hospital in Tokyo Bay. These all panels that you see are all carbon fiber reinforced panels. So how does fiber reinforced concrete work? And let me just give you a very quick historical perspective on where we were, in fact, 30 years ago and where we have come today, and how it's all kind of directed towards optimizing the material itself. Now, as you can imagine very easily, that the building block of any fiber reinforced concrete is that single fiber, as I was trying to think in terms of sort of micrometers and nanometers now, is that single fiber which is actually bridging the crack. So when you start analyzing that one single fiber which is now bridging the crack, and there's been a number of models that have been actually developed, which actually will tell you how does a fiber essentially pull out of the matrix. Because you're trying to reduce its or maximize its pull-out capacity. And when you're trying to maximize its pull-out capacity, you're also making sure that the fiber doesn't fracture in the process. So there have been a number of models that have been created actually to analyze these fibers. A number of patents actually that have been generated also are in designing these fibers which pull out at the highest resistance, but they really do not fracture in the process itself. And again, a fair bit of work that's been done here or in other places, generation of models, is on the surface chemistry itself. So if you look at any particular fiber, that would have essentially a very, very high contact angle with water. What we're trying to do is we're trying to coat these fibers by reducing and thereby reducing its contact angle, which means that the fiber becomes highly hydrophilic. And when a fiber becomes hydrophilic, it will absorb a lot more energy. And when it absorbs a lot more, or a better bond, so you can essentially see these polypropylene materials which have got a treatment with plasma, which can reduce, in fact, the contact angle quite substantially. So again, over the last 30 years, a number of new techniques have been generated to increase that performance of one single fiber, which actually is now pulling out at a very high pull-out force without actually fracturing. And there are other methods, actually, fiber deformations, silica fume use, surface modification, surfactant use, and there have been a number of issues actually around our studies that have actually allowed us to generate these fiber reinforced concrete materials, which have now the type of characteristics which I call an elastoplastic response. So now if you look at all of the work that has gone into generating fiber-reinforced concrete or optimizing these materials, what we can do is now we can, in the 30 years ago, we would have had a response which is what we call a softening response or a deflection softening response. But by understanding the mechanisms of these materials, what we can now get is what we call a strain hardening response. So you can get a material which almost behaves like steel. And you can actually create materials which now can bend. This is actually concrete, which can actually bend and carry more strain than up to 5 or 6%. The new class of materials that we are working here is what we call eco-friendly ductile cementitious composites, and these have tremendous, I would say, applications in earthquake engineering. So what you are creating is basically materials which have an elastoplastic response. So this is concrete, basically having an elastoplastic response. Normally, if you didn't have fiber reinforcement, this material would fracture here, and the load would drop very suddenly. But what we can do now is through micromechanical modeling, we can get a material which has got a very, very high energy absorption capacity, almost up to 5 to 6%. And this is, in fact, quite exciting because now you can use these materials for a number of purposes. And the great, in fact, benefit of making them eco-friendly is that these are utilizing, in fact, large amounts of industrial byproducts, such as fly ash, such as metakaolin, such as blast furnace slag. So we are trying to reduce the cement content. Cement, as you know, is a very dirty industry. It produces up to 7% of global greenhouse gas emission. So what we are trying to do is in these composites, we are trying to reduce cement as much as possible. So clearly, these are quite eco-friendly, and they are also highly ductile. And just to give you, look of what EDCC or eco-friendly ductile cementitious composites can do, these are statues that have been built in Canada or in Saskatchewan, Canada, basically just utilizing the EDCC I just described. Now, coming to earthquakes now and how we fit into this sort of the understanding of strain rate effects in concrete. If you look at basically what happens during the loading, you're looking at quasi-static testing, which is a 10 to the power minus 6 strain, traffic, which is 10 to the power minus 6 to minus 4, gas explosions. Earthquakes, which is what we are dealing with here, generally could have a strain rate which is between 5 times 10 to the power minus 3 to 5 times 10 to the power minus 1. So you're looking at possible strain rates which are up to, say, 10 to the power 3 greater than what the quasi-static rate would be. And I want to impress upon you today, basically, is that when you're looking at strain rates which are that high, the traditional understanding of concrete does not really apply. Which you need to understand, basically, is the strain rate sensitive models where that apply to concrete, steel, and other materials. And you can have basically this explosion, terrorism, those kinds of things may have actually a strain rate approaching almost 10 to the power 1. So how do we understand how these materials behave, or fiber-reinforced concrete behaves under high rates of loading? There are several methods available. There's the split Hopkinson pressure bar. This is actually from Tongji University. This is where I have some joint collaborative work where we are looking at understanding these materials, how they perform under high rates of loading. And this is a machine we have here at University of British Columbia. It's a drop tower whereby you can generate very high rates of loading and see how those EDCCs that I'm talking about would actually perform under high rates of loading. Now, typically, what we do understand is that the materials are highly sensitive to rate, and this is a synopsis of hundreds of test studies actually that have been performed, and you will notice that when I'm plotting, say, a response versus strain rate, what you will see is that it kind of performs in a bilinear manner. So you would have a knee in the curve here, and your earthquake loading is somewhere just before the knee or just after the knee. So just before it becomes highly sensitive or just before it becomes highly sensitive. And there's been a fair bit of work done on these materials under high rates of loading. Now, when you come to EDCCs, when I'm actually stressing these materials at rates of loading which will be associated with earthquakes, for example, 10 to the power minus 3 per second, that be the strain rate, you'll notice that this is my material which is under quasi-static conditions, and this is a material which is under dynamic conditions or earthquake-related conditions. And you will immediately notice that while I do see an increase in strength, as we saw in the previous curves, what I also see is that there is a drop in the strain capacity. What that means is I'm not able to absorb under those high rates of loading similar energy as I would have absorbed under slow rate loading, which means that there is a cause for concern here, that we really need to go back to understanding micromechanics better, develop better fibers which can continue my strain energy absorbing streak here further, and not really see this brittle response which is coming at approximately 1% strain, whereas I can actually strain this other material under quasi-static conditions to 5 to 6%. There's also an influence of size. So if you sort of prescribe to Bazan's size effect law, you'll notice that in fact the energy absorption capacity reduces as I'm actually increasing the size of the specimen. And you'll also notice that the curves become much steeper as I'm increasing the strain rate. What that means is size effect becomes even more important when you're having materials which are being strained at high rates of loading. This brings me to the last two topics that I want to briefly talk about. One was the infrastructure issues around the world. You have these pictures all over the world that infrastructure is deteriorating very rapidly, and it also would point out to a bridge collapse we had in Montreal, just outside of Montreal in 2006. Now, of course, these things happen, and one has to worry about how you analyze these highly deteriorated structures under an earthquake. But the biggest concern, I think, to me was that this bridge was inspected the same week it collapsed. What that means is we really do not have an understanding of how deteriorated these structures are, and what that requires is two things. One, it requires highly durable materials to build these bridges, and I will argue that in fact fiber-reinforced concrete is a very durable material. Secondly, we need to actually monitor these bridges by smart materials, or utilize smart materials that can interact with us and tell us that we are very close to failure just before the failure occurs. And I think to complicate issues further, there is also an issue of global climate change now. And we just finished a doctoral work thesis here, which looked at, in fact, in 7 large cities of the world, including Shanghai, how the global climate change will affect our concrete structures. So if you look at really our concrete structures that have been affected, if you look at now increase in the atmospheric CO2 levels from 370 to 1,000 ppm, which is what the scenario 4 tells you from the IPCC, you would definitely get an increased corrosion rate. You would get increased carbonation, which causes corrosion, as you know. Increase the temperatures by over 5 degrees Celsius. It will increase the shrinkage in materials, porous microstructure and hypermeability, and it will increase the corrosion rates further, and increase water levels. You get increased saturation, and you'll get greater scour, which means that you have foundation issues now with higher saturation and higher water levels. So some of the modeling that we have done, it indicates that in some cities like Bombay or Shanghai, the corrosion can actually start about 9 years sooner if you have this full-blown global climate change in the structure, which means that you also have another issue now to deal with, is the global climate change. So when you're using fiber-reinforced concrete, and this is the other study we performed where we looked at, in fact, time to corrosion as a result of use of fiber-reinforced concrete in the structure. And here is 3 elements. One is unloaded, one is 15 kilonewton loading, and one is very close to 30 kilonewton loading, which is very close to the capacity. As you can see that if I'm using plain concrete, 0.1 cellulose fiber, 0.3% cellulose, 0.1% polypropylene, and 0.3% polypropylene, you will notice that as I'm actually increasing the fiber content under one loading, the time to corrosion actually starts to increase, which that means is I can now derive a lot more from the structure before the corrosion actually takes over. So fiber-reinforced concrete being a very durable material, because of its crack control capacity, you can actually get a lot more years out of a structure as a result of fiber use. So, and also for repair side as well. If you're repairing these structures with fiber-reinforced concrete, one can easily predict that you would get a lot more life out of the structure by using fiber-reinforced concrete. So that brings me to the last topic. When you have these structures which are highly deteriorated, how do we actually create a scenario where these structures can talk back to us? And when the structures can talk back to us, you can essentially understand what the condition is and how far are we from approaching a certain collapse state. So in other words, what we're looking at is putting sensors on these structures. So you have this typical bridge. You can put certain sensors on it which can then correspond or interact with us over the internet. You can do sensing, you can do data acquisition, data processing, communication, damage detection, and then modeling and interpretation. And fiber-reinforced concrete, if utilized in structure, is a smart material. And I want to show you that you can actually get some data, significant amount of data, by essentially understanding what fiber-reinforced concrete can do. Here are some other sensors that we are using on structures. I'm sure many of you are familiar with this. But what I'm going to talk about is essentially a fiber-reinforced concrete type sensor, what we call a cement-based sensor, which are generally carrying carbon nanotubes. So these are materials actually. So you have these materials which have been stressed, and we're trying to generate a sensor out of these. And the sensor data actually is predicted using impedance. So these materials become highly conductive. And that conductive material, when you actually pass a current and put a stress on it, its impedance changes. What that means is if I have a material which has got, say, for example, multi-wall carbon nanotube, I have a material which has got a very high conductance or a very low resistance. And as I'm putting a certain stress on it, that material becomes extremely sensitive because its impedance will then change as a result of change in the stress level, which is what we call piezoresistivity. So in effect now, if you have a structure which has been then subjected to a cyclic load during an earthquake, for example, and I have a material which this structure is made of, if I'm monitoring its resistance, or if I'm monitoring its what we call frictional change in resistivity, this signal from the material itself will tell me, or it will mimic exactly what the structure is saying, which is wonderful because now I can just monitor the material, and the material will tell me what actual load is being actually carried by the material over the internet or over through some kind of a measurement device. So you can actually run, understand quite a bit about how the structure is actually performing. And these are some of the calibration curves from the materials that we are developing with nanotubes. Here's your traditional sensor. Traditional sensor, very linear. Here is your PFRC sensor, piezoresistive FRC with 15% fiber, nonlinear response, very high gauge factors, which is in fact an order of magnitude greater than your traditional gauges or electrical gauges that we use. And here is the other material which has got my multi-wall carbon nanotube. You can see that again the gauge factors are even higher than that, which means now you have a sensor which is extremely sensitive, and it can tell you very quickly what the stress level on the element is by simply hooking it up to an electrical inlet. Just to give you a brief view of where these sensors have gone, this is the Provincial Bridge in Winnipeg, Manitoba, which are carrying some of these sensors now. This is the actual control room just under the bridge, which is monitoring how the bridge is responding to traffic, etc. And now we can clearly see, if indeed we are closer to some kind of disaster, or if we are closer to closer to the capacity of any element, then these sensors will be very quickly telling us what the state of the structure itself is. That brings me to the end. Thank you for your attention.
Thank you very much. We're going to dispense with questions. We're running quite a bit behind. And the next speaker.
Thank you, Dennis. Good morning, ladies and gentlemen. This morning I will be presenting to you research conducted at University of Ottawa on seismic retrofit of reinforced concrete and masonry structures. As you know, seismic retrofit strategy can be implemented either at the element level or at the system level. If you have few substandard elements, lack strength and or ductility, then it makes sense to retrofit these individual elements. Typical examples would be columns, beams, walls and beam column connections. But if you do have a number of such non-ductile elements, then it makes sense to brace the entire structure, limit lateral deformations, and this also helps control non-structural damage. So the research projects that I will talk about are mostly within the scope of Canadian Seismic Research Network and involve both types of retrofit strategies. And we all know that columns play an important role, whether it's buildings or bridges, and first-story columns in a building or a bridge column are responsible for overall strength and stability of the entire structure. And typically columns suffer damage due to lack of transverse reinforcement. Here you see not enough transverse reinforcement and hence not enough diagonal tension capacity, or if you do not have sufficient transverse reinforcement, especially highly axially loaded columns, then of course you do not have the ductility that you wish to have in concrete, and lack of confinement provides another deficiency. And thirdly, lack of sufficient longitudinal reinforcement splicing causes a problem. And in the old practice of bridges, we would reduce lap splice lengths as low as 20 times bar diameter. And these happen to be in potential plastic hinge regions, obviously creating problems. So the first retrofit project that I will talk about involves use of FRPs, fiber reinforced polymers. Nowadays, of course, it's widely accepted in construction industry to use carbon fibers and glass fibers and wrap columns for all of those three deficiencies that I talked about. And the important point that I wish to make here is the importance of axial load, which distinguishes bridge columns from building columns. Typically, bridge columns are subjected to about 15% of concentric column capacity in terms of axial load. They're essentially bending elements. And in these columns, if you do provide transverse fiber wraps, then you're not really using potentials of these fibers. And columns fail through other mechanisms prior to reaching strength of the fibers. And here's an example of a square bridge column this time, and retrofitted with fiber jacketing, and it was able to go 4 to 5% drift. And then here is a building column which is subjected to 35% of P naught, which is typical of building column axial load level. And here we were able to rupture transverse reinforcement. And the current, or I should say previous design approaches did not consider axial load as a parameter for FRP jacket design. And hence a displacement-based design methodology was developed as a function of axial load, as a function of lateral drift capacity, and has been incorporated in CSA standard S806 in its 2011 edition. And it does provide fairly decent comparison if you do solve for the drift capacity, which is a design parameter, and compare it with experimentally observed drift capacity. There's fairly decent agreement. Now, the second technique that I would like to talk about is transverse pre-stressing of columns for enhanced strength and or deformability. As we all know, pre-stressing is not done in transverse direction, but this application is intended to introduce active pressure over and above passive pressure that we introduce through existing transverse reinforcement. And the technique can be implemented either one of the two ways. Firstly, we can use 7-wire strands and wrap the strands around them with ring anchors and pre-stress them to induce lateral transverse pressure. And in the case of square and rectangular columns, in order to take advantage of hoop tension, one needs to provide these razor elements. And obviously, eventually, you have to either cover it by shotcreting or provide some sort of column cover, not only for aesthetic reasons, but also for protection against corrosion. And here are some column specimens that have fiber reinforced covering on them, and this is essentially shotcreted on concrete, and they went as far as 7% drift before the cover started spalling off. Here are some examples of the improvements attained from this technique. Here you see a shear dominant bridge column, and typically shear dominant columns, if they do not have sufficient transverse reinforcement, cannot exceed 1% drift, which is not sufficient during earthquakes. But if you did apply this transverse pre-stressing, then you could go over 4% drift. And the level of pre-stressing depends on the type of performance you expect. If you want a crack-free column after a reasonable magnitude of earthquake, literally without any cracking, you can increase your transverse compression, which would overcome cracking of concrete. But obviously, subsequently, as the cracks start increasing, then reinforcing or the pre-stressing still kicks in as additional transverse reinforcement. So it does provide two functions. It improves V sub C term, the concrete resistance to diagonal tension. It also adds additional steel against shear. And this is a comparison now for confinement effectiveness of this combined active and passive lateral pressure. Here's again a bridge column, this time circular column, that was able to go up to 2% drift. Unlike what we think, reinforced concrete has inherent deformability, and this is unconfined column being able to go up to 2% drift. But at that time, it started, the cover started spalling off, and then the reinforcement rebar started buckling. But when we retrofit them with transverse pre-stressing, the performance improved, deformability went over 4% drift, and the damage on the column was extremely limited. Now, the third application is for inadequate splice region, and here's a bridge column which had typical pre-1970s practice with 20 times bar diameter located in potential plastic hinge regions. Beyond 1% drift, bars started slipping. You could see the pinching and hysteresis loops, and then obviously there was a strength decay. An application of transverse pre-stressing improved bond between steel and concrete and enhanced performance. By the way, in our CSA standard for FRP applications for square columns, use of FRP to control bar slippage is not permissible because you do not get similarly good behavior because you only rely on passive pressure and you cannot mobilize the entire hoop tension in square columns. And hence this technique has superiorities in that regard. Now, more recently, because of the special skills required for pre-stressing columns, we tried to use high-strength packaging straps to see if we can simplify this procedure. After all, we need lateral pressure and we need high-strength steel. The packaging straps that we typically use have up to 800 MPa strength, and they come up with handheld devices, and you can pull them and pre-stress them, and then they use what is known as seals to anchor them. And in the case of square and rectangular columns, instead of using steel razor discs as we did last time, this time we use precast concrete units and completed square columns to circular sections and rectangular columns to elliptical shapes. And then we got tremendously good behavior. Here you're looking at what used to be a rectangular column. Now it's an elliptical shape, retrofitted with transverse packaging straps, pre-stressed up to approximately 30% of the capacity and allowing some further expansion during earthquake. And you see improvements in hysteretic relationships as you compare those against unretrofitted columns. In the top left corner, we have flexure dominant circular column, and then bottom right corner was a shear dominant column because of this transverse pre-stressing mode of behavior change from a brittle shear mode to ductile flexural mode. Now I'd like to talk about system level interventions, and we do have obviously non-ductile reinforced concrete frames with and without masonry infills, and I'll be referring to some projects that involve converting non-ductile URM into a shear wall within reinforced concrete frame, and we will also talk about load-bearing masonry walls. And first of all, for bare frames, a conventional way of retrofitting them is either to fill it with reinforced concrete shear wall or provide steel sections as steel bracing. We have been researching use of pre-stressing strands and pre-stress these frames in the diagonal direction so that initially they're both in tension. As the frame sways in one direction, the tension side will become under increased tension, whereas compression side will start unloading itself and hence transferring load resistance from one side to the other, and that then improves effectiveness of pre-stressing strand. These are 1600 MPa 7-wire strands, and we did get quite a bit of improvement. We looked at having single 7-wire strand, double 7-wire strand, pre-stressed up to 100 kilonewtons, which corresponds to approximately 40 to 50% of rupturing strength. And then the black horizontal lines represent capacity of unretrofitted frame. As you can see, not only strength increased, but stiffness also increased because of diagonal pre-stressing, and we were able to resist higher loads under lower drift levels. And we are currently in the process of developing buckling restrained elements, BRBs, braces for reinforced concrete, unlike the typical BRBs that are used in industry, which consists of various size steel plates. We're looking at using bars. These are high-strength bars, and they are shaved inside the pipe to encourage the bar from yielding in that region so that there will be controlled yielding. And however, they're not allowed to buckle because of the exterior constraint provided by the pipe. This is an ongoing research now, and hence I will only show this picture. We have not yet assessed the results, but we did do one test, and we're in the process of doing another one now. We tested one typical of Ottawa seismic level, for which we use regular strength steel. Now we're testing one for twice the load, presumably representing a building in Vancouver, and the results will have to be assessed and made available later on. Now I would like to say a few words on masonry research, first starting with infill walls, and then we'll look at masonry alone. And we have done some research on use of surface-bonded carbon FRP sheets on infill masonry. The intent here was to convert this non-ductile infill masonry wall into an equivalent shear wall, which would act along with the enclosing frame, which then requires a lot of anchoring, and obviously when you do use surface-bonded, surface-mounted FRP, which is a very high-strength material, to masonry, which is low-strength, relatively low-quality material, there's incompatibility problem, and bond becomes a very significant issue, and hence we had to come up with homemade FRP anchors, and we used them to improve continuity. And here you see FRP anchors, which are essentially twisted anchors cut from FRP sheets and then inserted into holes, and that then provides continuity between surface-bonded FRP and the enclosing frame elements. Of course, we had to do a special separate study on FRP anchors and came up with a design methodology considering inclination of these anchors as well. Now here you see comparison of unretrofitted and retrofitted specimens, and using FRP did improve strength quite a bit, but then obviously we were not expecting too much ductility because you're combining brittle material like URM with brittle material like FRP. So retrofit strategy for this kind of application is bound to be for elastic strengthening rather than inelastic deformability. And then there was much debate on the cost of this type of application, so we tried to minimize use of FRP. Since then, FRPs are becoming at reasonable cost, and we used only a long diagonal tension, so X-bracing was the application. Everything else remained the same. In the previous application, of course, we have the side benefit of controlling infill walls against out-of-plane failures. This time there was that as well, but not as well as continuous coverage. And because total fiber area reduced this time, there was relatively lower strength gain, but this was still significant, at least double the unretrofitted strength. We also extended diagonal pre-stressing methodology to reinforced concrete walls with infills. This time infill was brick masonry as opposed to block masonry, and we again got quite a bit of improvement in strength and some ductility, because these pre-stressing strands being steel, of course, introduces some ductility. Now I'd like to go into individual load-bearing walls. The first one being reinforced concrete shear wall, isolated wall, and then unreinforced masonry and partially reinforced masonry, and talk about the technique of retrofitting them using steel strips. And these are steel strips provided to mimic a frame, in other words, vertical and horizontal direction, as well as provide bracing, in other words, providing diagonal steel strips in this manner. And these are roughly 2-meter tall walls. And very quickly, the top hysteretic relationship shows 1960s reinforced concrete wall, no boundary elements. The moment we pushed them beyond yield, then longitudinal bars started buckling, and then it started virtually rocking along the wall foundation interface. But when we used these strips to provide boundary elements, then there was some improvement, but further improvement was attained when we provided strips through by means of through bolts along the diagonals as well. Here's application on unreinforced masonry wall. The first wall essentially started rocking with very little strength, and obviously when you attach these strips and tie them to the foundation, there was quite a bit of strength enhancement. And the last one is for partially reinforced wall, and there was originally some strength, about 120, which went over 400 kilonewtons of lateral resistance due to the use of these strips. Finally, I'd like to show you two applications of surface-mounted FRP on masonry walls. The first one is, again, partially reinforced, nominal reinforcement, and we used FRP essentially to control shear as well as introduce some flexural capacity, because in earlier tests we saw that shear would follow immediately after rocking, and then there would be diagonal tension and toe crushing in masonry. So we essentially wanted to have diagonal elements in FRP, and then we also wanted to connect vertical FRP to foundation for flexural strengthening, and hence we used the same anchors in the way it is shown. The first application involved using anchors in diagonal direction provided with 30-degree inclination so that they would take tension in their longitudinal direction, as well as anchoring them in the foundation. We did get improvement. This is the wall test under reverse cyclic loading, but unfortunately the anchors were not placed right. The vertical anchors, they're supposed to be at least 2 inches or 50 millimeters, and they were short of that, and so the improvement in strength, flexural strength, was not as significant as we had hoped to attain, but diagonal strengthening was quite significant, and the red envelope curve indicates overall resistance and shear, whereas there has been quite a bit of improvement due to control of surface cracking. And finally, we combined use of FRP with ductile stainless steel plates. And these stainless steel plates are tremendously ductile materials, and we couldn't believe our eyes. We thought there was a mistake in our machine. And then we measured the elongation. Elongation was 60%. So you see the same coupon before and after testing, how much it has elongated, and yet it has not ruptured. So we put these steel plates inserted them into the foundation, having cut the foundation, and epoxy glued them. And then we also put some through bolts, small size threaded rods to control buckling under reverse cyclic loading. Here you see the application on the left-hand side, the plates inserted on the right-hand side, final layer of FRP covering them. And there was quite a bit of improvement, both strength and ductility. This was originally unreinforced masonry wall. This is completely URM, whereas the previous one was partially reinforced. And you could see the tremendous improvement in strength and ductility attained with these plates. This is all I have to say. Thank you for your attention.
Yes.
Well, thanks, Brad. Very interesting retrofits and many different types of elements. And we'll have to save the questions for the coffee break, which is coming up soon. Our next speaker is from Tongji University, Mr. Kong Zhen. Ms. Kong Zhen, speaking about computation analysis of shear wall structures. Welcome.
Can you use this one?
Well, they want you to use this because of the just thank you.
Thank you. Good morning, ladies and gentlemen. I'm very honored to be here. And my name is Chen Song, come from Tongji University. And my topic is computational analysis of shear wall structure with replaceable coupling beams. And this is the outline of my report. And first, I will introduce some important study in this research area. And then I will show you a simple tube model and analysis. And next, the benchmark model is repeated. And it's a real model with replaceable coupling beams. And finally, it's a summary of my report. First, as you all know, the collapse resistance design prevents structures from collapsing. But after strong earthquakes, the structure is difficult to repair and the repair time takes long. But the earthquake repairable design prevents structures from collapsing and concentrates the damage. And after strong earthquakes, the structure is easy and soon to repair. Under earthquake repairable design, the earthquake resilient structure are emerged, and the structural system with replaceable members is a typical type of the earthquake resilient structures. And the structural system with replaceable members is a type of structure in which replaceable members are installed to concentrate plastic deformation and dissipate earthquake energy, while the rest of the structure remains intact. Through this method, the use of the structure will not be affected, and the whole structure regains full capacity after replacement. And up to now, the researchers in this area focus on bridge system with replaceable cupping beams, replaceable members, and the frame system with replaceable members, and also the shower systems with replaceable members. First is the bridge system with replaceable members, and actually it's a new eastern span of the San Francisco Oakland Bay Bridge, and on the left you can see it's a bridge tower, and between the tower shafts are the replaceable shear links. The results show that the displacement is decreased, and the replaceable shear links can reduce base moment of the tower shaft. And next is the frame system with replaceable members. On the left is a replaceable cover plate with drilled holes, and it's a steel frame. The cover plate with drilled holes can avoid the weld brittle failure of beam to column connections, and research also shows that ductility is increased by 60%. And on the right is also a beam to column connection, and it's a replaceable slip damper, and the slip damper could dissipate 90% input energy, and the beam to column keep elastic during test. Also, it's a link column frame system, and as you all know, actually it's a brace system, and the linked column acts as a brace. The link column consists of replaceable links and dual columns. You can see the base shear is a contribution of the link column and the secondary moment frame. The reaction is a three-stage reaction, and you can see in this stage it's a rapid return to occupation. The linked column getting to plastic stage, but the second moment frame keeps it elastic. And in this stage, the linked column can concentrate the deformation, and the second moment frame can be intact. Then is the shear wall system with replaceable members. All the examples I talked about before is about steel structure, but this type of structure is about reinforced concrete structure. And you can see this is a reinforced concrete shear wall, and this is the replaceable foot, and it consists of laminated rubber, and it is designed to resist the pressure force, and also the mild steel plate. It is designed to resist the tension force. It's made by Tongji University, and also it's a reinforced concrete shear wall with replaceable cupping beams. It's also made by Tongji University, and the replaceable cupping beams is made of steel with low yield point. This type of structure is what I will talk about today. Shear wall system with replaceable coupling beams is a type of structure that you can replace reinforced concrete coupling beams with low yield point steel sheets. And under minor earthquakes, the use of the structure will not be affected, and the whole structure keeps elastic. And under the effect of relative strong earthquakes, the replaceable device located in the coupling beam is subject to damage loading, while the main structure remains intact after earthquake. And after strong earthquakes, the structure is easy to repair and regains capacity soon. Then I will show you the simple tube model. It's a simple model, and it's a 5-story model, and it's a replaceable coupling beams. The replaceable coupling beams is divided into the yield section in the middle and the non-yield section at ends. And first we decide the ordinary reinforced coupling beams. And for the comparison, we designed the two groups. For group A, the span to depth ratio is 5.3, and for group B, the span to depth ratio is 1.6. And then, according to this design principle, that is the moment resistance and the shear resistance of the non-yield section equal to that in the ordinary coupling beams, and the moment resistance of yield section equal to that in the ordinary coupling beams, but the shear resistance of the yield section less than or equal than to that in the ordinary coupling beams. And then we decided the yield section. The yield section is made of steel with low yield point to concentrate the formation. And first, the mode analysis was conducted, and it showed the mode shape of the OCB structure, and the RCB structure is the same. And then from the nature vibration period, we can see there is an increase of neutral vibration of period in the RCB structure, but compared with group A structures in group B, exhibit smaller difference. Then the partial analysis showed the damage is concentrated in the yield section of the replaceable coupling beams, but the non-yield section of RCB keeps intact. To compare further, we conducted the time history analysis, and this is earthquake wave we put into analysis. And for the elastic analysis, the peak acceleration is 70 Gauss, and for the non-elastic analysis, the peak acceleration is 400 Gauss. This is the spectra of the input earthquake waves, and the black one is the target spectra, and the red one is the mean spectra of the input earthquake waves. You can see there is a good fit of each other, and then the top displacement, can we see the displacement history is almost the same, and for the group B, the maximum difference of the top displacement is 11.5. And also for the interstory drift, we can see there is also an increase of displacement in the tube model with RCB, but proper design of RCB will decrease the difference, because you can see the difference in group B is much smaller than that in group A. For the internal force, for the peak acceleration of 400 Gauss, there is an decrease in the maximum base shear and the maximum base moment, also the maximum force of warpiers. So the proper design of RCB will reduce the stress of warpiers. Also, you can see the historic curve. We can see the RCB is shear yielding and exhibited good energy dissipation ability. Then is a benchmark model. It's a complex model with a structural system of RC tube and SRC frame. The total number of stories is 50, and the coupling beam height is 800 millimeters. This is plan, and this is the dimension of the structural members. Then the design methodology is below. First, we do analysis of benchmark model with ordinary coupling beams, and then we replace the coupling beams with grid strips. In this case, we replace the coupling beams in story 11 to 30, and we replaced all the X direction coupling beams, but just the middle column of coupling beams in the Y direction. Then we design the replaceable coupling beams according to the design principle I talked about before, and to get the benchmark model with replaceable coupling beams. Then the mode result also shows replacing the coupling beam do not change the fundamental mode of vibration. And from the period, we can see there is also an increase of neutral vibration period in benchmark R, and the increase of first period in X direction is greater than that in Y direction, because we have replaced all the X direction coupling beams, but we just replaced the middle column of coupling beams in Y direction. And finally, it's a summary of my report. And first, we design of an ordinary structure with a simple tube model and complex benchmark model. And then we design the replaceable coupling beams with a non-yield section and a yield section. Then we do replacement and computational analysis with software, SAP 2000 and Abacus. And finally, it's a comparison of the results of a mode, displacement, and internal force. Computational analysis of a replaceable coupling beam is preliminary research to have an overview of this new structure element. And from the analysis, we can conclude that first, RCB has the ability to replace the OCB with little change of strength and stiffness in the structure, which means it's not necessary to redesign the major structure. And second, RCB is able to concentrate damage in the yield section, which is easy to repair and replace. Third is proper design of RCB will decrease the difference of strength and stiffness, in addition to reduce the strength of wall piers. And thank you very much, and welcome to discussion.
Well, thank you very much. You're our first speaker that we had time, so that was well done. I was the worst, and you're the best so far. So we have time for a quick question if anybody has one. When you modeled the building, did you include the floor slab? Did you model the fact that the floor slabs are rigid in your model, or did you ignore the floor slabs?
I do the couple of the nodes in the same floor.
Okay,
So we
put them together.
Yeah.
Excellent. Okay, so you're modeling. Excellent. Very nice. Well, thanks again for a very clear presentation. Very nice. Thank you so much. Okay, and our last speaker is Rick Rabazi, who is going to show us some of his very interesting results on slender masonry shell.
Cool. Everyone, I'll be presenting some recent research conducted here at the University of British Columbia regarding the in-plane seismic behavior of reinforced masonry shear walls. So, of the various types of failure modes affecting these type of shear walls, that we will focus on the outer plane instability failure mechanism, which was first documented by Pauline Priestley. We want to. The reason that this mechanism is of particular importance is due to its unsubstantiated effect on the height-to-thickness ratio imposed by the Canadian Masonry Design Standard, CSA S304. Although this failure mechanism has had there's much evidence and research conducted on reinforced concrete shear walls, this is not the case for reinforced masonry shear walls. So the height-to-thickness ratios vary from 14 for moderately ductile shear walls to 20 for moderately ductile squat shear walls. And these restrictions are quite inhibitive on the use of reinforced masonry as a design material in Canada. And particularly so due to the National Building Code's stipulation that all post-disaster buildings, regardless of seismic risk, must use moderately ductile ductile walls in their construction. So design applications such as fire halls or police stations or pump stations, which were commonly built using masonry, are no longer viable applications. So this is a multi-phase research study, and the first phase is already complete. And it focused on the reverse cyclic testing of reinforced masonry columns, which represented the end zones of a reinforced masonry shear wall. The findings of the test showed that as we load the columns in tension, you'll have development of fairly wide cracks over the height of the plastic hinge. And upon reloading, during the load reversal, the reinforcement, the single layer of reinforcement, had to carry the entire compression load. And due to the natural low stiffness of the reinforcement, out-of-plane displacements would begin to occur in the column. And these would continue until the face shells would come into contact. And at this point, you'd have one of two paths to follow. The first path would be if this face shell contact occurred before a critical limit, which was found to be half the wall thickness, and that face shell contact would cause a stabilizing moment over the cross-section, which would act to decrease the out-of-plane displacement. If, however, this contact did not occur before this critical out-of-plane displacement, this critical limit occurred, what would happen is the displacements would continue in an unstable manner until failure would occur. So the second phase involves the in-plane seismic testing, or loading of full-scale reinforced masonry shear walls. And the goals were to establish rational criteria for the out-of-plane stability of these walls, and also to create some or establish some good height-to-thickness ratios, both economically and safely, for these walls, and to prepare recommendations on the mitigation, as well as mitigation of this failure mechanism, as well as recommendations for future design standards. So the two tests conducted so far were on the identical specimens with geometric properties, resulting in a height-to-thickness ratio of 27.1, which is about double the current Canadian limit on these walls, and aspect ratio 1.5. The vertical reinforcement ratio was 0.33% and consisted of two 50-millimeter diameter bars in the exterior, two cores of the wall, and four 10-millimeter diameter bars spread throughout the center. The horizontal reinforcement ratio consisted of a single 10-millimeter diameter bar at every course height, so every 200 millimeters. So there's two types of tests done on these walls. The first test was meant to simulate the bottom story of a multi-story structure, so it required the use of 3 actuators, with the 2 vertical actuators representing both the axial loads and the overturning moment from the stories above. And the second wall represented only the bottom story, or a single-story structure, say a warehouse, and did not require the use of these actuators, these 2 vertical ones. So the loading protocol was displacement-based and used a displacement increment, which had its basis in the lateral displacement causing reinforcement yielding in the most exterior bars. And all this was with axial load of constant axial load of 660 kilonewtons. Looking at the response, you can see that it's fairly elastic until we had some splitting and toe crushing at this north end. And this continued on with additional face shell spalling and crushing at the toes, until eventually we had failure, compression failure, but it was after significant damage that occurred at the toes. So looking at the axial strains, which were determined to be quite important, we had around 2 times the yield strain in the most exterior reinforcing bars at the failure. So our key findings were that the failure mechanism was actually toe crushing. Really, it wasn't what we were looking for, but and that the high axial load prevented the important development of wide and uniform flexural cracks over the plastic hinge height. Even though there were high plastic tensile strains, these were quite localized in the bottom two courses of the wall, which was not enough. So looking at the objectives for the second test, based on these findings, what we found is that we had to remove the axial stresses to create a larger, or to create those uniform wide flexural cracks over the height, and in turn also increase the large plastic tensile strains in reinforcement. And of course, because we're reducing the axial load, we had to now be aware of sliding shear at the base. So looking at the loading protocol for the second test, it was quite similar to the first test. In fact, identical initially, except for the much greater ductilities caused us to keep on going for quite a long time. And with this test, there was no axial load. So looking at the response, it was quite better, much better. There wasn't much damage until actually the base sliding at the toe caused the toe to extend past the footing, which is my design error, the footing reinforcement, and caused cover spalling of the footing. And this caused some asymmetry in the response, but toe crushing continued on both sides of the toe afterward. And the facial spalling actually allowed us to see the straightening of the reinforcing bars when in tension, and then the buckling of these bars when in compression. And this continued for a number of cycles until eventually we actually did get our desired, or at least partially desired, outer plane instability failure mechanism. So looking specifically, here's some pictures of the mechanism here. Looking specifically at the mechanism itself, we can see that very early on we had the outer plane displacements greater than anything seen in the first test, which were on the order of around 5 millimeters. And as you can see, very soon after load reversals, when you get these large outer plane displacements developing, and they continue until you get the face shells coming into contact, and upon which the restoring moment causes these displacements to decrease again. So looking at the overall response, you can see that the outer plane displacements occur at a pretty low, quite low lateral load, which confirms the first phase's results, as well as the maximum outer plane displacement occurring at around 0 lateral displacement, which corresponds to a low axial strain, which also confirms the first phase's results. So as you can see, this behavior continued for a number of cycles until that critical the critical limit of the outer plane displacement in half the wall thickness was reached, upon which the outer plane displacements became unstable. Looking at the axial strains, we can see that, again, they go up to around 5 times the yield strain in the most exterior reinforcement, and so quite a bit more than the first test. Our key findings here were that the outer plane instability occurred at high ductility levels, and that the failure was characterized by the large vertical tensile strains, and when the outer plane displacements increased beyond that critical limit of half the wall thickness. The absence of the applied axial load seemed to increase the probability of this failure happening. And although the outer plane displacements were observed at low ductility levels, they did not become critical until much later on. Looking at the comparison of the responses of the first test, W1 in red here, and W2 in blue, you can see that there's quite a bit of difference in ductility anyways, and a little bit in the lateral load capacity. The overturning moment is quite higher in the first test, but still the ductility is much more in the second test. Looking at the outer plane displacements versus lateral displacement and the outer plane displacement versus axial strain, you can see that the W1, the first test, is that the amount of outer plane displacements quite insignificant compared to the second test. So our conclusions are that out-of-plane instability is a possible failure mechanism in reinforced masonry shear walls, and that instability occurs at very high tensile strains, but it must occur over wide and uniform flexural cracks. The applied axial load apparently does have a quite significant effect on the failure mechanism, and that out-of-plane displacements they initiate at low ductility levels, but they do not become critical until later on. And that it is also quite apparent that the height-to-thickness ratio in itself is not sufficient to assess the stability of reinforced masonry shear walls. So future phases possibly we will be looking at are, again, to further investigate these parameters affecting out-of-plane stability of reinforced masonry shear walls, and also to use these parameters to develop ways to mitigate against this mechanism occurring. Right now, next set of tests we could possibly be looking at determining critical axial stress, which helps to prevent this mechanism occurring in these walls, and also to explore the use of better confinement in toe regions, which was found to be very important. Another one would be looking at the different types of reinforcement layouts, which we believe will actually will significantly affect this type of mechanism occurring. And that's it for that. Yeah.
Thank you, Brooke, for an excellent presentation and for staying definitely within the time. And so we will have maybe a couple of quick questions. I have one for you, which is, so the placement of the vertical steel in the wall is obviously going to be critical. Mm-hmm. So, I mean, did you place it perfectly in the middle? And then what are your comments about real field conditions where it might end up on one side?
Yeah, that's exactly right. In our walls, we did quite a good job of keeping it with very low eccentricity, but in the column test, the first phase, it was significantly there's a significant amount of eccentricity in the column. And working on this beginning phase of analytical study, it is important, very important mechanism, or parameter.
Any other questions for Brooke?